It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to Unit 4, where we're going to leave our polynomials behind that we've spent the past, 4 months talking about, and we're going to move on to trigonometry, and we're going to get hashtag Triggy with it. So let's get to it. Today's lesson is all about making sure we remember stuff from last year in geometry. So consider the following triangle. So I get to play geometry teacher today, which is fantastic because I never get to do that. Where the measure of angle A and the measure of angle D are 30. So A is 30 degrees and D is also 30 degrees. What do we know about these two triangles? Well, notice that they're both right triangles, and if this angle's 30, well, that tells me they have two angles that are the same. They have two congruent angles. And last year we talked about that triangle ABC would also be similar to triangle DEF by angle. We know that they're similar because they have those two congruent angles there. I have a right angle and a 30-degree angle, and therefore I also have the third angle is the same. So when two triangles have congruent angle, corresponding angles are congruent, that tells me that they're similar by angle. And if we notice here, there exists a dilation that maps triangle ABC onto triangle DEF. If I double AB, I get DE times 2 and times 2. So there's this multiplier, there's this dilation factor of 2 that would somehow map triangle ABC onto triangle DE, proving to me that they're also similar. So these triangles are similar because they have two congruent corresponding angles. So compute these ratios: CB over AC. So CB over AC is 1 over 2. And then I want to compute EF over FD. So FE over, I actually want to do DF here just to keep things correct. That'd be 2 over 4, which is also known as 1/2. So notice that these ratios, CB over AC, is the same as FE over DF. Those two ratios are equal, which makes sense because in similar triangles, the corresponding sides are in proportion. Those two ratios are going to be equal. 1/2 is the same as 2/4. So notice what this means. That's what this 30-degree angle is doing here. This 30-degree angle is setting it up so that these respective sides always have a ratio of 1/2. So if I had another triangle here with another right triangle with a 30-degree angle, that tells me that these two sides are always in a ratio of 1/2. So if I had this as smiley face, well, this was 2 and that's 4. This over here is going to be 2 smiley face. 1, that became 2. 2, it became 4. So what this does is this sets up this ratio where if I find the ratio of those two sides, smiley face over 2 smiley faces, you always end up getting 1/2. So we define that ratio here as the sine of 30 degrees. So we say the sine of 30 degrees is 1/2. That ratio, regardless of how big the triangle actually gets, the ratio between the opposite side from 30 and the hypotenuse here, the ratio between the opposite side and the hypotenuse for this 30-degree angle, regardless of what triangle you're in, is always 1/2. And that's what trigonometry boils down to. Trigonometry boils down to similar triangles and knowing that this one angle in a right triangle determines actually all three sides of the right triangle, determines the ratio of those two sides. We don't know how big the triangle actually is, but I know the ratio of those two sides depending on what trigonometric function we use. So right now we have let any angle theta, this is the Greek letter theta, and we're going to be saying that a lot this unit. Let theta be an acute angle in a right triangle. And we have our three trig functions. We have sine, cosine, and tangent, defined as such. The sine of an angle is opposite over hypotenuse. The cosine of an angle, don't say cos, don't say sin, it's sine and cosine. The sine of an angle and the cosine of an angle, cosine is adjacent over hypotenuse, a over h, and tangent, the tangent of my angle is opposite over adjacent. So those are our three trigonometric ratios, sine, cosine, tangent. You used them last year a whole bunch. We still need to know that sine's opposite over hypotenuse, cosine's adjacent over hypotenuse, and tangent is the ratio of opposite to adjacent. So the key idea with these trigonometric functions is that they are functions. Just like I say f of x, I'm going to say sine of theta. I input an angle measure, that's my input. This is the name of the function, I'm using the sine function there. We input an angle, and it outputs a ratio. That's how these work. We always input an angle measure into a trig function, and it always equals the ratio of two sides. I don't know what these two sides are here, but the sine of that angle equals opposite over hypotenuse. It equals a ratio. So that's the thing. Trigonometry still deals with functions, which is why we study it in Algebra 2. I give you an input, and then you have to find me an output. So consider right triangle ABC where the measure of angle A is 30 degrees. Use this triangle to find these values. So when I deal with a triangle, I'm working with 30 degrees here. I label it. The first thing I label is my hypotenuse, which is across from my right angle. And then I label my opposite side, which is opposite the angle, which leaves me with my last side, my other leg being the adjacent side. So it just takes knowing what these ratios are. When I input a 30 into the sine function, sine is opposite over hypotenuse, 1/2. Cosine is for my mnemonic people out there, TOA, adjacent and hypotenuse. It's the ratio between the adjacent and the hypotenuse. And then my tangent, the tangent of my angle, opposite over adjacent. Okay, so once you identify what angle you're sitting at, it's always helpful to label your sides and know whose hypotenuse is obvious because it's across from the right angle, but don't forget to label your opposite and your adjacent. Using the same right triangle, let's do the sine, cosine, tangent of 60. Well, if this was 30 degrees, donde está el 60-degree ángulo? Well, it happens to be up here, right? If this is 30 and 90, how many degrees are left over? Well, I need to get to 180, so 60 degrees does it. But notice, since I'm sitting up here this time, notice that now my hypotenuse never changes, but notice my opposite side has now changed, which makes 1 the adjacent. So now that I labeled my triangles, I can find the sine, cosine, and tangent of 60. The sine of 60 is opposite over hypotenuse. The cosine is adjacent over hypotenuse. And the tangent is opposite over adjacent, which is just radical 3. And finally, using triangle DEF, let's find sine, cosine, and tangent of 45. So let's pause the video here and see if you can do this on your own. So here's my 45-degree angle. That right there is my hypotenuse, opposite, and my adjacent. So the sine of 45, opposite over hypotenuse, 1 over radical 2. Cosine, adjacent over hypotenuse, is also 1 over radical 2. 45 degrees is a special angle where sine and cosine, the sine and cosine of that angle are equal. And the tangent of 45, opposite over adjacent, is 1. Quick little side note, got a little side note here. Quick little side note. when I have a square root in the bottom, a lot of the times we multiply by that square root on the top and bottom. This is really the number 1 here. So I'm not changing the value of this expression, I'm just changing the way that it looks. So I get the square root of 2, right, over radical of 2. Radical 2 is radical 4, which is 2. So notice this is equivalent to that answer there. A lot of the times that's what you'll see in multiple choice questions, is we get the square root out of the bottom. The way that we do that is we multiply by 1. We take that square root and we multiply it on the top and bottom, and that ends my side note. La. All right, moving on here. Hopefully this is review here. Let's look at number 4 here. Consider right triangle ABC shown below. I'm considering it. ABC, it's a right triangle. Find sine of theta, cosine of theta, and tangent of theta. So I need the sine of theta. Well, there's my angle. Let's label hypotenuse. That's opposite. Go across. Ooh, ouch. I have 2 sides of the right triangle. If only I knew how to find the third. If only some dead Greek guy told me how to deal with the sides of a right triangle. Oh wait, Pythagoras, our good friend Pythagoras did tell us this. You're all saying right now a squared plus b squared equals c squared is the Pythagorean theorem. I don't like that because you don't know what the heck a, b, and c are. So I go leg squared plus leg squared. Those are the 2 sides of the right triangle. Equal the hippopotamus squared. There's your hypotenuse. So leg squared plus leg squared equals the hypotenuse squared. So we're going to be doing this a whole bunch in this unit. So we're going to have leg squared plus the other leg squared should equal the hypotenuse squared. And what I mean we're doing it a whole lot, I really mean that. Like every problem we will be doing the Pythagorean theorem. So 25 plus x squared is 169. I'm going to subtract my 25. Willow is barking in the background saying hi to all of you. 144. And we square root and we get 12. So I can always find the third side of a right triangle, and we're going to do that a lot. So my adjacent side is 12. And now we just find the ratios. The sine opposite over hypotenuse. Cosine adjacent over hypotenuse. And the tangent of theta. Get good at drawing theta. I draw a circle and then just keep on going through. The tangent of theta is opposite over adjacent. There we go. We did it. Nice. So our friend Pythagoras is going to come up a whole bunch. Leg squared plus leg squared equals hypotenuse squared. So consider a right triangle with acute angle theta. Let me draw a right triangle. Right triangle, acute angle theta. Such that the sine of theta, they're giving me information here, is the ratio is 7 to 9. Sine is opposite over hypotenuse. So in my triangle, the ratio of these 2 sides, this side to this side, needs to be 7 over 9. 7 over 9. That's what we're going to do. However, I do want you to realize that it could be any similar triangle. It could be 14 out of 18. It could be 70 out of 90. All of these triangles have that ratio of 7 to 9. I don't know how big the triangle is, so we'll just assume it's the numbers we see. 7 to 9 make our lives easier. If I see sine is 7/9, well, opposite is 7, hypotenuse is 9, but know that it could be any multiple of those numbers, as long as it's the same multiple for both sides. But I digress. Find me cosine and tangent. Well, we ran into that problem again. I've got 2 sides of my right triangle. My friend Pythagoras will help me find the third. Leg squared plus leg squared equals the hypotenuse squared. I have opposite and hypotenuse and need to find my adjacent. So 49 plus x squared equals 81. Subtracting that 49 over, oh goodness, this is getting tough. 32. Square root it. I get x equals the square root of 32, but I'm going to go over here to scrapland and split that up. How do I split that up? It's a really big chicken nugget we're in right now. 36, 32. 16 and 2. So it's really 4 radical 2. A lot of the times it'll ask for simplest radical form. So this side over here is really 4 square roots of 2. I don't know why that pen is so thin. 4 square roots of 2. So a lot of the times we're going to draw pictures, do some Pythagorean theorem, and then comes the trigonometry. The cosine of my angle and the tangent of my angle are SOH opposite over hypotenuse, 4 radical 2 over 9, and then tangent opposite over adjacent, 7 over 4 radical 2, which you could fix up by multiplying by radical 2 over radical 2, but I don't care. I love it, someone said in a song once, so we'll just leave it as such. Draw a picture, Pythagorean Theorem, SOHCAHTOA. That's our game plan for most of this unit. Draw a picture, good old Pythagoras, SOHCAHTOA. Let P be a 0.68. All right, let's find the 0.68. 6, 8. It went over 6 and up 8. Let theta be the angle formed by a ray that passes through the origin and P. So a ray is not a line segment, it's a part of a line segment, part line. One side has a starting point, the other side has an arrow that goes on forever. That's what makes it a ray. And the angle theta is right here. There's my triangle. I went over 6 and up 8. So find the sine, cosine, and tangent of this angle. Well, look what I've got here. My picture's all set. So now I can do leg squared plus leg squared equals hippopotamus squared. Leg squared plus leg squared equals the hypotenuse squared. 36 plus 64 equals x squared. That's 100. What squared is 100? Well, that's 10. The hypotenuse there is 10. So now I can find my sine, cosine, and tangent of angle theta. Sine of theta, cosine of theta. And my thetas, you'll see, generally get worse and worse as I draw them. That sine theta there is atrocious. We'll fix it a little bit better. Sine, all right. Here's my right angle. There's my hypotenuse. So sine is opposite over hypotenuse. 8/10. Well, that's 4/5. Cosine, adjacent over hypotenuse, 6/10. Well, yeah, you're right, 6/10, which is also 3/5. And then tangent, opposite over adjacent, 8/6, which is 4/3. So these are my ratios. Those are my final answer. Draw a picture, Pythagorean Theorem, SOHCAHTOA. And finally, number 7 here. Consider a triangle such that AB is 2, BC is 4, and B is a right angle. Draw a picture. B is a right angle. ABC doesn't matter. AB is 2. BC is 4. Determine the value of sine, cosine, and tangent at angle A. There is my angle there. Well, draw a picture. Got to do a little Pythag here. Leg squared plus leg squared equals the hypotenuse squared. 16 plus 4 is x squared. 20 is x squared. So we square root and get, I can split that. Radical 4, radical 5. So 2 square root 5. Now that I'm all set, I can find the value of sine, cosine, and tangent of angle A, which I've renamed theta. Sine of theta, opposite over hypotenuse. Cosine theta, adjacent over hypotenuse. And tangent theta, opposite over adjacent, 4 over 2. Now again, you can clean up these fractions a little bit. 2 over radical 5. 1 over radical 5 and 2. And again, you can get those radical 5s out of the bottom by doing that. And again, I don't like doing that because it's an extra step, but you can do that. I choose not to most of the times, unless it's a multiple choice, and you might not see this. You will see that. So again, that's our quick review of SOHCAHTOA, of sine, cosine, and tangent from geometry. That's all we need to know going forward to get us through the month of January, where we're going to explore trigonometric functions a whole lot more. So again, draw a picture, use a little Pythagorean theorem, and then find me some ratios. Go get them, folks.